Hello, my name is Qubix, and I'm pleased to see you here in the seminar room for one of the seminars on revision. This instance, I'm talking about doing rasterization the old school way. So maybe you remember last year I gave a seminar about 3D geometry engines, and this is a continuation of that seminar. So I would want to make a quick reminder where the rasterization is part of the rendering pipeline, and also give a good explanation why we need rasterization at all. That's not quite clear. And from that being said, I would start with the humble beginnings with the Bresenham step algorithms that are quite commonplace, and then going to 3D and how surfaces are being rendered with polygon fillers, and going to shader algorithms up to the point what I would consider the holy grail of the non-CPO area, the perspective correct texture mapping. And I will also give a small outlook what we can expect when we put the intersection theorem the other way around. So this is more or less what I was also talking about last year. The visualization of animated 3D scenarios is a key discipline in the demo scene, and all that being put up and to give the artist's imagination a view into the real world, we first do the geometry, and then we put everything on screen with graphics primitives. And this screen nowadays mostly consists of picture elements. We call them pixels. And points, lines, circles, surfaces are mathematical objects, and to put them on screen, we need to discretize them. They are continuous mathematical objects, and we do a rasterization to display them on screen. Well, do we really need this? That's the question. And actually, it's not really necessary. We can also work without a rasterization. It's just an artifact of the display method. And there are nice counterexamples. Here we have the Vectrex console, which renders graphics purely using analog electronics, and then without steps. And also, it's in principle and scope being built into the Vectrex. And we had also a nice demo last year that also showed how to draw graphics without rasterization. So one of the first things one encounters when one wants to draw high-res graphics on a computer are how to render a line on screen. And you would normally take the formula y is m times x plus b from what we know from middle school. And there is a better way to write it, because we don't have any artifacts when either the line is going completely steep. And the idea is we step along one axis and determine the best fitting value of the other axis. And the Bresenham algorithms manage that without using floating point numbers. They work already with integer numbers. If we want to do this with circles or ellipses, we need a second-degree polynomial. I've written that down, and be assured that's about the only slide in this seminar with a formula. And it's a little bit easier if one of the coefficients is 0, then that means the circle or ellipse is axis aligned. But last year I used BASIC to prototype the geometry engine, and this time, language of choice is C. I'm using C here mainly for its capabilities, so it's much easier to express ideas. You are more problem-oriented rather than implementation-oriented. And I'm using C here for, in a sense, two different platforms, namely for the VIC-20, so 8-bit, and C is possible on the VIC-20 with cross-compiling. And there's also another library I'm using that is in principle compilable on anything that has a C compiler. So what is the C part of minigraphic? So minigraphic is a graphic extension for the VIC-20, which was originally written by Wolfgang Wirth and had been published in a German 64er magazine. And I already used it at that time. And when I rehashed my VIC-20 ideas, I thought that would be a good base to re-implement with a bigger graphics screen. And minigraphic really means you have a minimal set of graphics commands and functions and a defined file format. And it even got some third-party support over the years in Vice with Recoil. And last year, I got an idea to port that library, which formerly, and still is, of course, a basic extension to C. So it's more approachable for the people. And the other part, so the C image processing library, this is originated as a means to process image data within image processing suite called DBS ad oculos. And here we have only pure memory-based bitmaps, but they can be serialized as files. And this small library has support for grayscale, RGB, and floating point bitmaps, and makes use of the Unix portable graymap and portable pixmap file formats. And you can use any viewer you like to just view that pictures that have been constructed or calculated with that library. And again, it's just a minimal set of graphics primitives being provided and mostly supplied as macros, but client programs should compile on pretty much everything that has a C compiler. So what I would also like to rehash is the viewport clipping. In last year's seminar, I went and just avoided that problem. So I just chose an object to display on screen that didn't introduce any clipping. And I just want to remind you, you need to do this when you are going to 3D. So when we go to display surfaces and want to fill things, well, then the first thing we need is a polygon renderer. And at first, that looks like a simple task. You just have to draw the lines around the polygon. You maybe have to think about what happens when those lines overlap or cross. And then you need to decide what is supposed to be filled. What doesn't work is fill the outline, draw the outline, and make a float fill, because that doesn't work. You can have self-intersection, and then you don't have a good inner point in the polygon to fill. You can have acute angles, and then you don't potentially fill the whole polygon. So you can only work on the geometric data. And you have also maybe the issue that the vertices may be given with sub-pixel accuracy, and Bresenham in its most basic form doesn't support that. And finally, you could also have polygons sharing edges, and for many algorithms, you need that these sharing edges should not be result in multiple pixels, making an overlap from the two polygons. And ideally, the result should look like this. And this is a single path. These are, let's count, 12 corners, and they have been combined into one single object, and I'm using the even-odd rule. So if you come from the outside and go over one of those lines, then it's being filled, and if you go over an even number of lines, it doesn't get filled. And the algorithm for this is being part of a binary and source text package that I will release when this seminar is complete. So the next thing would then be, well, okay, spheres are boring. A torus is somewhat a more interesting object for what I am going to achieve. And if we have a curved surface, the normal method is to triangulate it, because what stands on three legs, that stands, and triangles are flat. We use simply that polygon renderer for the case n equals 3. We do a visibility check with the cross product. This is one of the methods. I use that cross product on the already projected coordinates. And even if we have the wireframe being shown, we see with a torus, it's a non-convex object, and you get overlap of surfaces. And we have to deal with that. You see here, that's the torus with the triangulation, and you see in the middle there are some triangles that need to be overpainted during the process. So the first method we would use to show the torus would be flat shading, and I use the simple shading method here for the moment. I just use the mean triangle ray position as a depth Q, and more advances would be to use Lambertian reflectance, but that requires calculating the normals on each of the vertices and then calculating the dot product. And it's a little bit, it's complicated, more complicated, but it's really not necessary to show the torus. And if we do this, we get this. So this is a torus rendered with flat shading, with just going with the grayscales from the back to the front, and you clearly see the 3D model. What you already also can see is there is our brain working on enhancing contrast. It's a purely end-optic effect that depends also a little bit on the display, but if you take some of the surfaces you see, there is an extra contrast which actually is being built by the eye. And of course, you see all those facets. And that only shows how good our brain is being able to interpret such images. And there had been another step algorithm being invented by another mathematician, Henry Gouraud. And he thought about an improved shading method. So not just doing the same intensity across the whole triangles, but to interpolate the corner intensities over the whole triangle. And this, again, works with any given lighting model. And well, you still have to watch out for the correct gamma exponent for the display and also for Mach lines. And again, this is an end-optic effect, and it might not show up that well on the display, but let's see how it works out. So this is Gouraud shading. And actually, what I see more here are efficiencies of the beamer. So this is 256 gray intensities, and with a good display, you are being able to make out lines like a grid across the torus. And again, these are our eyes, our retina that enhances the contrast. And also, if you have just a low polygon count and use improved lighting models, then Gouraud shading might lose the highlights. That's the reason there had also been invented another shading method, the Phong shading. I thought about including that here, but actually, even with Phong shading, you still get the facets around here. And for this reason, I omitted it from this seminar. So how does Gouraud shading work? We interpolate the intensity linearly over the triangle, and that's always possible. We have a linear function of the intensity. We have three parameters. We have three intensities for each triangle point. These give a linear equation system with three unknowns, and that can always be solved unless the lines, the triangle vertices are in one line, and then the triangle is invisible and you just don't draw it. So you can always think about, you take the 2 points with the lowest intensity and the highest intensity, and then you linearly interpolate. And the third point can only always be set between those two intensities by skewing that gradient you see here. That's always possible. And then you have a linear interpolation here and also a linear interpolation here. And this example had actually been rendered on a VIC-20. So I wanted to include the other possible lighting models. You can use the vector dot product between the normal vector and the light ray. And here we have the three rendering methods, the flat shading, the Gouraud shading, and the Phong shading. And as I said, the gamma exponent and the Mach bands. So, and last year I got asked whether perspective corrective texture mapping would be possible on 8-bit. Yes, it is entirely possible. And as I said last year, in the end, you need 2 divisions per pixel, and this is slow unless you have a GPU. And well, it's so you have 9 parameters you need to fit. And if you map a quadrangle to another quadrangle, you have 8 equations. They can be easily been found out, but they are also part of the package I will put online after the seminar. You have 1 free parameter. You can set one of the denominators to 0 for the target middle point, to 0 to 1 for the target middle point. If you are using float, if you are doing this with integer, it's more sensible to use a power of 2 for this. So what got me intrigued into texture mapping actually, that had been an article in a Happy Computer in 1988. So that showed this picture, and I found it quite interesting, the idea to arbitrarily distort a picture. And actually, that was an earlier example I found about texture mapping. And as I say, it already was in 1988, so a little bit before, say, Doom or those other programs that also showed textured content, textured polygons on the screen. And I also had the ambition to replicate that effect on a Commodore C128. And the first attempt I tried at that time, say really in 1988, was quite disappointing because I fell prey to the idea to use bilinear mapping for this. And it does not work because you get this. If you do a bilinear mapping, you are, in a sense, linearly interpolating into the texture along all edges. And if you then connect the corresponding points and fill in, you get this. And this red line, this red diagonal is supposed to be a straight line. It isn't. That does not work. What we want is this. And you get this when you use the formulas I gave the few slides earlier. And as I said, it's entirely possible also on 8-bit machines. And I use the VIC-20 as a stand-in for all 8-bitters because it's perceived as a very weak 8-bit machine. It actually isn't. There are always surprises. But it is slow. You can see how the chessboard is being drawn when you execute the program. It's also part of the package. And you get this result. It's not. This is possible on other 8-bit machines as well. And as I said, without GPU, there's really no good chance. I can tell I tried to program also at the time, I tried to program it on an Acorn Archimedes. And even there, you can still see that a single polygon, a single quadrangle is being rendered. And it only gets fast if you use interpolation. So and those were the tricks that were pioneered with those ego shooters. But anyhow, even if you don't use a GPU, you can still make use of such a program because you have the direct control over the math. And I included that example program that rendered that correct checkerboard that is also being part in the package. So I said earlier that I wouldn't include Phong shading. And we could also use another method that concentrates not anymore on triangulation, but we construct the view rays from all pixels of the display window. And if we do that, we get a ray tracer. And this is entirely what is in principle necessary to handle curved surfaces. And the only thing you need to know is how is your surface being expressed as this formula type. And if we do it with a torus, we can now compute the intensity for each single pixel. We don't do any simplifications anymore. We can use any given lighting model with diffuse rendering, with Lambertian lighting, with reflection, with transmission. Everything's possible. But for a torus, you already need to handle fourth-degree polynomials. And they can be solved. And if I want to have a torus that goes into an arbitrary position in the room and is rotated in any possible orientation, you need to compute 35 different numbers, and it's easy to get those formulas wrong, but the result is worth it. You get this. No triangle. This is every single pixel is being constructed from rays, going from the observer, and you can put in any lighting model, any material model that you want. You can tessellate the room and put the texture on the torus. And as I said, that's also been included and a way for you and something for you to play with. All these examples aren't fast at the moment. They are expressed in C, and they are supposed to serve to give an insight into the necessary math that is being used to draw all these pictures. If you want to get it fast, then you can use the methods I showed you in the first seminar last year. And I really think what I will now show you is how the Gouraud shaded torus is being drawn on a VIC-20. That should be possible to render much faster if the methods from last year are applied. So maybe I would guess something about 1 frame per second should be possible. That what I want to leave as an exercise for the viewers. So, all these demonstration programs were rendered using C libraries and programs. The demonstration programs will be published in the VIC-20 denial forums. And check out this URL. Thank you all for your attention, and have fun at the revision. And just takes a few moments, and then we'll start up the rendering process on the emulated VIC-20. So, first of all, it should. Okay, I see. Do we get a picture? This is just the standard desktop that should show now. Okay. Let's see. Do I need to restart? Let's see. Okay.
Are there questions from the audience?
Yeah. So, yeah.
Sorry, you said that the first algorithm, Bechenstein,
Bresenham.
yeah, that one works with integers only. Generally, if you have an algorithm which only works with integers, you use rounding, right?
Yeah.
Can you tell me how it's handled in that algorithm?
Yeah, okay. So actually, you have an error term when you make the decisions between stepping along the long part of the line, and that error term is being initialized with a given number. So the first step up already happens in half the time. That normally happens during most of the line in the middle. So, and that is what is mostly being used to round the pixel steps. So you have, in a sense, when you are using Bresenham, you have two different lengths of line strips in the middle, and you just need to make sure that the ends are half that length in the ends. So, and then you have the nearest positions along each one of the smaller extent of the line. It's I have put also an implementation of Bresenham in the libraries, and they can be show. They're just box standard implementations of Bresenham, and it uses the error term in a way. So as I said, that you make the first step already a bit earlier than the other ones.
Okay, danke.
Bitte.
Earlier on in the presentation, you mentioned doing floating point bitmaps. I'm curious why you would want to have floating point bitmaps in the first place, because that's not something I've ever encountered before.
Yeah, that's actually part of that image processing library, and some of the images you might calculate when you are doing more complex image processing. Then byte accuracy for a single pixel simply isn't enough. I use this image processing library to do pattern matching, and to speed up that pattern matching, I use the methods of Fourier optics, and this implies that I do Fourier transformations on images, and then the results are not anymore easily boundable by the range 0 to 255. You just need the whole lot of float numbers in a wide range, and you are just happy to have the floats around. So, actually that algorithm was sped up by a factor of like 200 by using the methods of Fourier optics. This is not my screen. I see something else. Let's see. That is the other one. Okay, that solution. Okay, that gives me the opportunity to, okay. Sometimes problems have simple solutions. Just take a little bit working with two screens. So, and when I went to do that example for the WIC20, I was quite unfortunate because I actually wanted to have everything in one program, and that's not possible with that setup using C. It should be easily go within one single executable if you do the necessary extra work and apply the methods of last year's seminar. So Okay, let's see. So drag around this as well. And here we have the first part that does the calculations with the geometry engine, and it takes time. So I'm allowed to use warp mode here. And what the program does, it calculates all vertices, it makes a triangulation, and it sorts the triangles. And then you get this result. Quick 20. So, and I've prepared it this way because it's also so the C compiler in question doesn't use doesn't provide a C runtime that's capable of returning back to basic, and so to get the coordinates into the next step, I need to do a reset. And I'm storing the coordinates and the triangles in a safe space. So when I now go and change into another directory, so I should also disable warp mode. I simply change to another directory that is being used as disk. And this part has the nicety, we will already see it working right from the beginning. It is slow, but it works. You see, at first, the back parts of the torus are being rendered, and then it comes forward. And just meditate a little bit, say another 10 seconds about that. You see, it's built up. And then we put on the next gear. Remember, I'm of course cheating now regarding the speed, but we want to see the result in a variable time for the seminar, so there we go. This is on a VIC-20. Gouraud shading is also possible on 8-bit machines. Are there any further questions?
I mean, this is pretty slow, obviously. How much potential do you see when you rewrite some of the stuff from C into assembly code? And also, second questions, what about accelerating the mathematics with lookup tables?
So both being put in one kind. In last year's seminar, I was using lookup tables and meshing code all over. So you won't need much more precision, or you can, in a sense, use the same precision that I also used for the cube example in the last year. And that went with, let's say, 70 frames or 25 frames per second. We have here not 8 vertices, but 288. So we are already, when we are just talking about the number of vertices, we are already 2 orders of magnitude more. So we can't expect to do frames per second. Just from this standpoint, maybe 1 frame per second would be okay. And then we are not only drawing lines, but we are filling triangles. We need to draw the lines, and the filling comes extra. So I would say this example needs roughly 3 minutes in real time. I need to check, and I suppose it could still be made a factor of, say, 50 faster when going to machine language completely, and that would mean you can render this in a matter of a few seconds.
Okay, thank you.
I would like to ask, could you also do this with, for example, Q8.8 fixed point to get better
That's
accuracy?
actually being used, sort of.
Nice.
Actually, in last year, I used 2.6 fixed point to speed up things. So that led to an easy realization of the fixed point multiplication. I just could multiply two 8-bit numbers together and get 4.12 intermediate result and discard the upper bits, the upper 2 bits and the lower 6 bits. And that had been all laid out in last year's seminar. So that's what I say. If you apply the methods of last year's seminar, you should be able to render this thing in a few seconds. Everything faster, and it would be really, happily surprised if that was being possible to draw within 1 second or so. And of course, the routines I give there, the drawing routine, are somewhat specialized for the VIC-20, but the primitives are encapsulated, and it should also be possible without any issue, without any big issue, to port the routines to the Apple II or to other 8-bit machines. There exist implementations for VCC, which I'm using here, that are also compile code for the other 8-bit machines. So, in a sense, if you are doing all those, graphics rendering on a machine that doesn't have GPU, you always have to think out what is necessary before you proceed to machine language. I went all through this for the Qubix example in the last year, and this time, I think it's a nice exercise for the viewer to take a look at the programs and then do the transition himself.
You said there are 35 coefficients in this computation, so...
For the torus, when you ray trace it, yes.
Okay, so and in this example, so the first part of the program,
yeah.
Can you just change the angles and it would compute it again without changing formulas or something?
That's entirely possible. That's part that you have two angles that are sensibly being used, because if you turn it around this way, nothing changes from an apparent view. Yeah. Really parameterized, yes. So, any case, they are for rotating torus, of course. So, yeah, thank you all. So, thanks for being here, and have a good time at the party.